Hi everyone. So since nobody have joined up till now, we will start the class. It will be available in the recording. So uh, so this is week 3 and we would be solving some tutorial problem. This will be uh, very like to the question which will be asked in the assignment. And so assignments are also in the same format of quiz where you have to pick up the choices. And let's start. Just checking if everything all right. Okay. So our first problem is we're in a beam problem, which of the following is primary variable? And we have four options: displacement, shear stress, bending moment, none of the above. Now let's consider equations of beam. So in fact, the beam which will be solving is called Euler-Bernoulli beam. So in Euler-Bernoulli beam, there is a function Wx which satisfy the differential equation. Double differentiation of respect to x. Okay, so this was the first question where in a beam problem, which of the following is the primary variable, and hence I was defining the beam problem. So in our Euler-Bernoulli beam, there is the equation of Wx and it's in this form. Qx is the forcing function. Let me draw the figure. So this is cantilever beam, and this cantilever beam is subjected to arbitrary loading. Let me define arbitrary loading. So let's say this is the arbitrary loading in downward direction. So similarly, it is distributed as such. Okay. Okay. So there is a doubt like in FEM, shape function can be one second, can be different from polynomial. Yes, shape function can be different from polynomial. So let's say there is a polynomial. We can take trigonometric equation, trigonometric equation. Also, we can take exponential equation. So sum of something which is converging. Okay. So main thing about the yes, yes. So polynomial, why it is preferred? Because it can be uh, it can be find into a very beautiful structure such as matrix. So it can be easily defined by the matrix. And if we take the exponential function, then there are one more additional step to it. But hence this is more preferred, the polynomial. As we will go further in the course, we will see that these shape function, which are polynomial, they are kind of treated in form of matrices. All right, the matrix is the important thing by which it is more preferred. I hope it's clear. Okay, okay, I will carry on with this. So we have a Bernoulli beam. So this is the governing equation, and the figure I was making. So what is happening at the end is there are two forces. So one is F naught, okay, and there is one more forces at this moment. So there are two forces. One is at the end, the F naught as well as M naught. So this is a moment called M naught and force called F naught. And this thing is Qx, and this is the first end which is fixed. Uh, and these are the direction, the coordinate system. So this is direction of Z and W, and this direction is X. Okay, so I hope all the sign conventions would be clear. And if we take very small element, let's say if we are taking only this much element, and if we enlarge it, let's say that is that element with having some arbitrary loading. So now that loading will become rectangular in nature. So this is our loading Qx, and we are defining some sign convention. So you would be remember the sagging and hogging thing. So it's something like that. What are the relations? Relations are dm by dx is v, and dv by dx is equal to minus q, which is our loading, and which gives us Castigliano theorem. So just for the sign convention, I have written all these. Okay. So this is cantilever beam with a set of loads. So this is our whole picture. The question was asked like which of the following is primary variable. So we will look at now. As you can see, this equation is a fourth order, with fourth order derivative, and now first we have to convert it into some other form, and so we have to multiply it using some weight function, and then so let me copy paste the equation. This is our governing equation. Now what we will do is we will multiply this whole equation with weight function, and we will integrate in the domain from 0 to L, and then uh, dx is equal to 0. So this is our uh, weighted residual form. Next what we will do, we will integrate it twice. So we will get something like this. V is our weight function. This into dx, and so we are integrating it twice, and when we are integrating twice, we will have some other terms also. The final solution I am writing here. From limit 0 to L. Now, if we integrate it one more time, here a comment about b. B is function of x, hence we are not taking it outside. It's not a constant respect to x. D by dx with this b, and otherwise we would have taken it outside. Yes, 0 to L. So upon differentiating twice and applying the integration by parts, we get that in this last line there is, so in the last line we can see that it follows the where, let me highlight it, where this function, like whatever is outside this integral, that should be 0. Uh, so which gives us our boundary condition. So if we take d by dx, only this term, so it is kind of third order. So this is generally the shear force in bending problem. And it, if we take only double differentiation or second order, then it's called bending moment. So these two constitute a, okay, of this equation, which is the weak form formulation. So this is weighted residual, and then yes, so this is weak form, like this final form is weak form. This is our weak form. It gives each and every information about the system. So specification on the W and dW by dx is considered the essential boundary condition, and specification of the shear force and bending moment, it constitutes the natural boundary condition. Now let's consider our boundary condition by the condition given. So you can see it is fixed at this end. Since it's fixed at this end, hence W at 0 is equal to 0, and dW by dx at x equal to 0 is equal to 0. So these are the two conditions which we will we can say that the essential boundary conditions are given like this, as well as at this point The shear force is given as minus F naught d by Tx b of dw. This is given as minus F naught as well as bending moment is also given as minus M naught. So at this end, all these data are known. Hence, also we know that essential boundary conditions are defined for primary variables. So hence we get our primary variable as w and dw by dx. So w is our displacement. To be specific, it's transverse or the bending displacement, how much z in z direction it goes, it deforms, and also the slope. So in question it's asked like which of the following is a primary variable. So there could be two answers. A slope, if it had been given, that could be also one of the answers. So displacement and slope are the primary variables. The remaining boundary conditions are called natural boundary conditions, and the whatever is there, it have some physical meaning to it, as we will see in the further questions. So this complete our question number 1. Okay. Now coming to question number 2. So in solid mechanics, which is quasi-static problem. So first we will look at what quasi-static problem means. The minimization of dash will help in finding the solution. So first, what quasi-static problem means? Quasi-static problem means like the load is applied so slowly that the structure deforms very slowly. So there is a deformation with respect to time, but it is very slow. What it results is in very low strain rate. That is our key point. Like there is very low strain rate, hence therefore the inertia forces is very small and can be ignored. So that is the main function by which we can ignore the inertia function. So you would have seen this equation, right? For some force. It is a simple vibration equation without any damping. So in this, these forces are very less. So these are ignored because of very low strain rate, and hence whatever is left is kx is equal to f. Okay. So our problem of such nature is called quasi-static problem. Any doubt on this? What is quasi-static problem? So this is called dynamic problem, and actually static problem is kx equal to f. So what we do, we so this is a transition which is called quasi-static problem. Okay. Okay. So uh, now there is something called principle of virtual work. The statement is if a body is in equilibrium. So the notion of equilibrium, it changes when it's a dynamic and when it's a static. So static has only one equilibrium, but dynamic has, it could have multiple equilibrium. So what quasi-static do is try to take each and every instant as a equilibrium. So there is something called minimization of the potential energy, and it is based on the principle of virtual work. And okay, the principle of virtual work in its full form can be written as if a body is in equilibrium under the action of prescribed external force. So there is some external force and the body is in equilibrium. Okay, that this part is understood. The work done by these forces in a small additional displacement. Now what we do is we give some small additional displacement and then which is compatible to the geometrical constraints, okay, and which is equal to the change in strain energies. That is the basic uh, mm, statement of virtual work, principle of virtual work. So this, whatever additional displacement we are providing, we call it as uh, virtual displacement, okay. So in mathematical form, it can be written as the variation of this external uh, work due to this external virtual displacement is equal to the change in the strain energy. And so this relationship is not generally linear, but for small displacements, we can assume it as linear. Mm. So that is the key point of quasi-static problem. And what principle of minimization of potential energy is that in this equation only we do like this. So this problem is nothing but minimization problem. Okay, okay. So this is principle of minimum potential energy. So whose statement is, so among all deformations or deformation configuration. Since we are talking about variation, so deformation configuration word is used. It is compatible with the geometric constraint. So this geometric constraint, due to the geometric constraint, the system is non-linear. But what we do, we take very small displacements, and hence everything becomes linear in linear regime. Hence the use of word quasi-static. So this is a statement of minimization of potential energy. So among all the deformation configuration which are compatible with the geometric constraint, the configuration which satisfy the equation of equilibrium is the one which minimizes the potential energy. So this is the equivalency between the principle of virtue of and principle of minimum potential energy. This is principle of minimum potential energy. These are equivalent statements. Okay. So in solid mechanics, the minimization of the potential energy will help us in finding the solution. So which completes our question 2 discussion. Any doubt till now? You can always write in the chat. Okay. Now moving on to the third question. So in third question is fairly simple one. If you have taken the or done the lectures, so here it's like EA represent. Now E is Young modulus and A is cross section area and U is displacement. So in this equation, if you'll see there is a second order equation. So okay, okay. So there is one more question, and it is how do you calculate strain energy from the curve stress strain? All right. Okay. So uh, to the address the question, I'm taking a separate page. Okay. So here, so what is the basic uh, way to tackle the deformation question is, so these undeformed coordinates. So we will take two coordinates, okay? One which is undeformed coordinate. So the body when it's not in the deformation, and then if we will talk, then we will take undeformed coordinates, and there is something called deformed coordinates. Now the choice of this deformed coordinates is dependent on how much strain or stress it can we can take. Okay, so if there is some very simple body such as our eraser, which is very elastic in nature, as you had seen. So let's say this is Apsara eraser. Okay, and so before deformation, it would be having some coordinate system. So let's say this is that coordinate system. Okay, let's say x, y, and z. And let's say after some time, this eraser is deformed. So let me draw the deformed eraser. The actual deformation and what we are uh, approximating using some model are two different things. Okay, it depends like how much accuracy we want. So if I need um, very high accuracy, then we go for something like method such as finite element method. So, it would be somewhere here. So the blue one is the deformed one, and black one is our undeformed. Okay, so the assumptions such as plane section will remain plane, or we only look at the only one deformation direction, or for example, this eraser can deform in z direction as well as in x direction as well as in y direction. It can deform in all the directions. But for this case, I have just taken that it is deforming in z and x direction. In y direction, there is no movement. All right. So now what will happen that I will make relationship between these two quantities, undeformed coordinates and the deformed coordinates, okay, and which will give me the strain relationship. All right, are you getting it? So which will give us the strain relationship. So this is how we calculate the strain energy. All right, and this strain energy is purely dependent on how much accuracy we want, because this transformation, if we will say transformation, is very non-linear in nature. So we have to provide some ordering scheme by which we have to eliminate many terms. So here what the engineers are more capable of doing. And so it's not like you throw everything to the computer and it will solve and you will get nice solution. No, the computer will, it also takes headache to solve very simple problem in very crude manner. Okay, so if we take very small mesh and uh, ask computer to solve each and everything, it would be requiring very high um capacity of computer. But if you're intelligent enough and you're applying some engineering concepts so that you can provide better approximations you can tell them so to the computer, then it will help the computer to easily solve and so that uh, it doesn't waste time, all right, the computer. So that's what the approximation and strain relationship have in the relationship. So, okay. So in this fairly straightforward question, EA represent what? That was the question, but actually here the question is asked in the another manner by which if we take any second order equation which is in this form, so this is very common form and in different fields it have different meaning. Okay, it's like you have one equation and you are just relating physical um, some physics to it. Okay, so for example, like if we take cables are the, it can be telephone wire or anything, okay, which are hanging by its by two poles maybe. So in which the primary variable will be our transverse reflections so which is nothing but u. Okay, u in this governing equation. The coefficient A could be tension. Okay, and the source term F, which will be distributed force, is distributed vertical force here. And secondary variable is axial force. So the so this is only for cables. Now if we take some other situation such as bars, so this question is of for from bars only. Now the primary variable is longitudinal displacement, and our coefficient A is now EA. Okay, and our source term is distributed axial force. Similarly, in different other fields such as heat transfer, this equation is there. Then when there is something flowing in a pipe, then also this equation is you can see whenever there is some electrostatics, then also these equations are can be seen. So the EA, if you will go for unit and dimension method also, you will say it will be having the unit of force. All right. Okay. Now we will look at question number 4, in which of the which of the boundary conditions need not to be satisfied by the approximation function chosen for the primary variable in case of weak formulation of the following differential equation. So a differential equation is given, and first we have to find its weak formulation. So finding weak formulation. So for 0 x, so I will do nothing, just the weighted residual form, and then integrate it. So let's say W is our weight function. So if we integrate, if we use integrate by part 1, this equation will be converted in Q, and there will be some additional term. So our question is which cannot be possible. So first of all, the option 1 is essential boundary condition. Option 2 is also essential boundary condition. Option 4 is also essential boundary condition. Okay, how we know what is essential boundary condition? Because it would have three. The boundary conditions will be of form or u of, so something like this, as well as at x equal to L. So it will be of either this form or this form, or it could be mix also. Like, so our question is which. So it should be for primary variable. So primary variable, we know primary variable here is u, and secondary variable is, can somebody say what the secondary variable is here? Anyone? So generally the secondary variable have uh, some some meaning to the question. Okay, for example, here is the axial force. Oh, is so this Q naught was our some axial force. So this only gives that the third option. So it is the only option which is not defined for primary variable but for secondary variable. Now moving on to the next question. Any doubt up till now? So next question is relating the Rayleigh method and weight function. So in Rayleigh method, which of the following option cannot be used a weight function when the primary variable is 0 at x equal to 0 and x equal to 1. So we know that whatever conditions primary variables are having is called essential boundary condition, and as the name suggests, why it's essential, because what is the meaning of essential is that must be satisfied. Okay, so hence for weight functions also, so what are these essential boundary conditions? Right, so let's say u at x equal to 0 is 0 and u of x equal to 1 0, and let's say w is some weight function. Now the relationship should be w at x equal to 0 should be 0 and w at x equal to 1 again should be 0. So out of these functions we have to check whether which one is not uh, 0 at both conditions. So we can see that sine 0 is 0, sine pi is also 0. So this is not our option. Second is x. So this is again 0 at both. This is not. So option C, because it is x0 is 0 at 0, but is it 1 at 1? I hope it's clear. The weight function should satisfy the essential boundary condition. Okay. Now we will look at the next question. Yes. Okay. 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 So first of all, we have to look at what weight functions mean. All right. So to give a feeling about weight function, let me draw a figure. It will take less time only. So let's say there are 2 points. Let's say the pointer A and at B. And there is some function u of x. Alright. Now what I am doing is I am taking one function which is following this. I am calling it w of x. Okay. Now the combination of this I'm saying is something like this, which I'm calling as u dash x. So the combined thing what I'm saying is u dash of x is equal to u of x plus w of x. Okay. So this w of x is nothing but variation in u. Look at it carefully. Like this w of x is a weight function and it's a variation in u. So what u dash of x is approximated solution, and u of x is exact solution, and remaining is weight function or variation in u. Okay. So what is how we can define this del? So del is the operator which is not equal to dx. So del x or del of u is not equal to d of u. I think this is clear to you, right? So what del u is, the del u of a function u, it represents an admissible function. Admissible change, sorry. So you can see that admissible means up to which we can work, and approximated solution is what we are approximating using different method, and exact solution, so there is very less difference in approximate solution, exact solution, that we call as variation, and it is term of calculus of variation. Just be with me, get the doubt will be clear. Uh, so if we consider at a particular x, then del u is the change in the admissible change. Okay. The key point is the variation of u is 0 at boundaries, because specified value cannot be varied. It's like we don't know how the function is uh, apart from the boundaries. Boundary we know, hence the weight function we know, so that is equal to 0. So hence this is our point. Alright. So the question which was saying that which of the following option cannot be used at weight function when primary variable is 0. So if primary variable is 0, then the weight function should also be 0. So in other term we call this essential boundary condition, but it is having the same meaning. Alright, I hope it's clear now. Okay. Now next question is nothing but regarding the properties of variation. So variation and differentiation is is something which is lot have confusion in it. So the properties are nearly same. For example, this property, like the differentiation can come out of the variation, variation is can come out of the. So this is something called like a ghost property. Anything can come out of anything. Okay. Now same with integration. How integration and variations are having the relationship. Other is something same as the differentiation. So this is something called chain rule. Now question 7 is which of the following is not correct? First is natural boundary condition is imposed on the derivative of the primary variable. So I think so. As you have seen in the previous question, here, yes, here. So this was our natural boundary condition, and as you can see, it is imposed on the derivative. So this is true. So this is true. The essential boundary condition is always homogeneous. So this I have told you that it could be of mixed type also. The essential boundary condition is imposed in the primary variable. True. Essential boundary condition had to be satisfied no matter what form of differential equation. True. So our answer is B. Now our final question is for today is in the beam problem, if displacements at both ends are known, okay, then so they will be referred as natural boundary conditions. No, those are essential boundary conditions. They must be homogeneous to solve the problem. Is it? So they could be mixed also. So hence it could be non-homogeneous also. It is written must. So must is not there. Okay. It can be, it cannot. Now they will be referred as essential boundary condition. Yes. Okay. So this gives us the end of our tutorial lecture. Any doubt? I'm still here for 5 minutes. Okay. What do you mean by homogeneous? So homogeneous means I have example of homogeneous boundary condition. Just wait. Yes. Okay. So I will just give an example of non-homogeneous. So what does it mean is derivative as well as the variable both are present in a same condition. So something like this. Uh, so this was our natural boundary condition in one of the equations. Now what I'm doing is I'm adding one more. Let's say u infinity is some constant, beta is some constant. So like this is derivative and this is just the variable. So this is primary variable and this is secondary variable, both in same equation. So that is called mixed formulation. Okay, and if there is no mix, then it's called homogeneous. So my meaning is homogeneous boundary condition mean du by dx is something, or at u it's something defined. Okay, one or zero, or u not. Okay. This will be also defined at some x. Okay. So these are called boundary condition. Any other question? Okay. So if there are no other question, I think we can end the class. Thank you guys. Okay. This is my WhatsApp phone number, so you can WhatsApp me or call me. Prefer WhatsApp. Okay, Vijay. So I'm ending the class. Thank you. Bye bye.